Start. So good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, for those of you that don't know me, and I'm still the interim director of NITheCS. This afternoon, it's an absolute pleasure to introduce Professor Bruce Bassett. Bruce is a professor, full professor of applied mathematics at UCT, and is also involved with SAAO. Yeah. But he studied at UCT, but did his PhD between Italy and Oxford. That's why he speaks a brilliant Italian. Yeah. But in 2004 or so, he came back to South Africa, and since 2008 is at UCT in that role. Yeah. And Bruce has been in charge of artificial intelligence in all matters SKA for a long time. And he's probably one of our better experts in the nearest surroundings. Let's put it that way. Yeah. So Bruce, we are really happy that you are here this afternoon, and we are very keen to hear when general artificial intelligence will eat us up.
Thanks,
yeah,
Francesco.
thank you.
Thank you. Thanks so much for coming. So I first gave a version of this talk about 11 years ago. So this has been quite a long journey for me. Hopefully an entertaining one for you. So I'll start my talk by this tweet in 2019 from OpenAI, when they changed from being open and non-profit to being semi-open and semi-non-profit. The new structure will allow us to raise enough money to build AGI. And Whiteson, who's at Oxford, was like, expressed the sentiment that many people had at the time. This was completely divorced from reality. And I actually checked with him recently about whether he still stands by that after ChatGPT. And he said, yes, sure. I still think we're very far from AGI. But of course, you now have people like the NVIDIA CEO saying, oh, I think we'll have AGI within 5 years. And at the extreme, you have people like Yudkowsky, who for a long time has been very concerned about AI, saying AI may destroy us in just 2 years. I have a sense that our current remaining timeline looks more like 5 years than 50 years. So it's an interesting place that we find ourselves with, all the way from the whole of humanity has 2 more years, which I think is probably a bit exaggerated, all the way down to, no, don't worry. And that will definitely come back, you know, to try to tease out the reasons for that is the thing, something that I'll spend a lot of time thinking about. So why are we even talking about AGI? I think a nice way to show it is this data plot. So on the x-axis, you got publication date. Y-axis, it's the amount of training compute in petaflops, floating point operations. And if we focus down here, Transformer, 7,500 petaflops in 2017. And now the latest Gemini Ultra, 50 billion petaflops. So that's a 7 million-fold increase in compute in 7 years. And that's a roughly 200 times more power. But you can see that's an amazing. You get 7 million increase for only 200 times the cost. And I think largely that's what's been driving things. And what's interesting is in the early days, there were universities who were, you know, leading the way. But of course, since about 2019, it's been private multinationals all the way, which is potentially a real concern, especially for universities. But of course, it's also only the biggest multinationals in the world, i.e. not Africa, that are able to do this. A more graphical way to show why we might be thinking about AGI, this is an image I made in 2022. A year later, the exact same prompt. I can't remember exactly what the prompt was, but a year later, the same prompt led to that. And then a year later, it had changed to this. So just visually, the improvement is quite extraordinary. Here's an example that shocked me just recently. I was doing some work with an art gallery in Cape Town, and we were exploring the use of ChatGPT to understand images. So I said, oh, what do you see here? And it described, oh, there's a book. And then it started to talk about the content. And I was like, it's just hallucinating the content. But actually, what I realized is it was reading the text. Okay, so I was like, wait a minute, actually, just tell me word for word what is in that text. And it said, sure, this is one of those rare books that can change the way we think by revealing, etc. So, and it was perfect, right? So that's, I think, remarkable, its ability to understand images. Text is not aligned, it's small, it's fuzzy. The image wasn't particularly high quality. I thought that was quite extraordinary. So one of the things that I think, of course, is really powerful about what's going on is a sense of universality. This is an AI-generated desktop from the 1970s, hallucinated. If you look carefully, you'll see that the typewriter keys don't really have letters. They have kind of vague squiggles. But the key point is you had a typewriter, a phone, a calculator, a Rolodex, a dictaphone. They were all separate objects. And of course, all of those have been subsumed into a single laptop. That's the whole point about universal Turing machines. They can do every type of calculation. So can I just check how many people would consider themselves to not really be experts in AI? Okay. How many people know, yeah, sorry, that's a bit of a loaded question. How many people not sure what a neural network is, how it actually works? Okay, couple. So let me just give you a very crude demo. This is from 3 Blue 1 Brown, a wonderful YouTube content creator. So the idea, for example, let's imagine we want to be able to classify handwritten digits. So we all immediately recognize that this is a 3. No, I'm kidding, that's a 9. Okay, but how do you know it's a 9 and not a 3? Okay, there's some very sophisticated things going on in your head, even though it seems completely trivial. Well, the way that a neural network works is it breaks this up into pixels. And in fact, in this image, there are 781 pixels, and it just takes the value of the pixel, how bright it is from 0 to 1, and puts it into a long row. And then it sends that information through this complicated network. And so it then sends the data through this network and gradually learns, as you train this network, it gradually learns what to look at. So here it's learned that important things are circles and straight lines. And each one of these little lines represents a number. Each one of these lines represents a number called a weight that the machine has to learn. And that's what we mean by training a neural network, is we have to learn all of these numbers. Once you've learned all those numbers, the network will make a prediction when you give it a new example. And GPT-4, for example, actually, I suddenly forgot how many parameters it has, but the big networks now are getting towards having 1 trillion parameters. So there wouldn't be just a few thousand like you can see here, there'd be 1 trillion parameters. So and of course, these are inspired by the brain, trying to model at least loosely what goes on in the brain. And that's, well, I'll come back to the point I was just about to make. Okay, let's see. So let's go through a bit about what have been the big breakthroughs in AI. And by the way, if anyone has any questions, just please stop me and ask. Don't worry about waiting today. And if anything's not clear, just interrupt me. People often say that, but don't really mean it, but I really do mean it. So one of the big breakthroughs in AI was the idea of converting everything to vectors. And a vector is just a list of numbers. And actually, this essentially implements Wittgenstein's vision of what meaning is for words. If you ask, what does a giraffe mean, or any word mean, for Wittgenstein, it was the meaning of a word is its use in the language. In other words, you can tell a word by the company it keeps. So for example, if we have the sentence, the cat sat on the mat, and the other sentence, the cat sat on the carpet, the fact that you can find examples where the only difference is that one word, cat and carpet, suggests that there's a strong link between carpet and cat. You can sort of use them interchangeably. And the more often you can see them interchanged, the closer the relationship. And the less often you see them interchanged, the less they are related. So the cat sat on the porcupine, not an obvious thing to see. So porcupine and Matt probably don't have a connection. So basically, the trick was behind a lot of the breakthroughs behind ChatGPT, but also many others, is that with every word, you associate a list of numbers. Okay, and the point is these numbers are learned by analyzing trillions of sentences, or at least billions of sentences, and essentially you end up with what's called a word embedding. And in this vector space, sorry, I don't know how technical everyone is, but I'm going to assume some familiarity with mathematical concepts. You end up with a vector space created by these vectors. And the cool thing is that words that are similar end up in similar places in this embedding space. So houses has nothing to do with cats or kittens. So it's way off there. Cats and kittens are down here and not too far away from dogs, because dogs and cats are both living beings, even though they're not that similar. And the nice thing about this is that once you have a vector, you can start to do mathematical operations on it. So you can add them and subtract them. So you could ask the vector man minus woman turns out to be basically parallel to the vector king minus queen. Okay, I'm just going to stop there because I'm sure there must be a question, because I've gone through that pretty quick. Yeah, so what you would do is you would typically pick the dimensionality of the space. You might say 760. And then what you would do is essentially learn all of these components. For every word, you would try to learn the components. And the way that you do it is you try to match the observed frequencies of correlations between words. So that's the thing that matters, correlations. So if you say hot, what's the most likely next word? Dog, day, that sort of thing. So trying to match the observed correlation structure, you can learn, incredibly, you can actually learn representations. So you're essentially learning to map a word into a vector space, and that mapping is controlled by a neural network itself, word to vec, for example. But yeah, remarkable thing. And it allows you to do things like that. Oh, sorry, other question. Yeah. You need a lot of data. Oh, yeah, sorry. The question was, could we just start from one word, or do we need to start from a collection? You have to start from a collection because, for example, imagine you go to another country and there's a language you don't, and someone just says the word to you, like, skoyatolo. And you're like, okay, what is this? And you have no context, it has no meaning. So it's only as a collection of structured sentences that you can actually pull out these correlations and hence learn the vectors. Good question. Not very sensitive. But in one way, yeah, but to quantify that is not trivial. Since ChatGPT is based on this, that's probably your best answer. How often does ChatGPT give you terrible results? But maybe we can move on. Okay, so the nice thing is you can start to say, what do you get if you take Paris, subtract France, and add Italy? What do you think is the vector that's nearest to that vector addition? Rome, exactly. What about bigger minus big plus cold? Waiting to make sure there's always a few people get it very quickly, but or sushi minus Japan plus Germany. Actually, that one's not so obvious. Okay. So if you go and look at this, you can ask, which is in the space, I've got a vector corresponding to the left-hand side, and you can ask, what's the nearest vector word to that vector? And that gives you your answer. So you can actually essentially answer simple questions like, oh, what is the equivalent of sushi in Germany? Anyway, you can do this. You get Rome, Colder, Bratwurst, AU, Android, etc. So the amazing thing is that you suddenly are able to do mathematics with linguistics. 10 years ago, or maybe 15 years ago, the idea of doing mathematical linguistics was not very common. So the cool thing is it's universal. You can do it for text. We've been talking about this, but you can also do it for audio. You can take a piece of audio and you can map it into a vector space. And then you can do addition of audio pieces or subtraction. You can do it for images, which is how Midjourney, etc. make images. And you can do it for video. So it's really universal. And because you now have a vector space for all of these, you can match across different modes. You can say, I'm going to take a vector from text and ask which is the image that is closest to it. Okay, which is how, these images that I showed you earlier are produced. And here's an example video. So the prompt is a man and a woman in their 20s are dining in a futuristic restaurant materialized out of nanotech and ferrofluids. So that text gets converted into a vector, and then it gets matched to a vector that then gets converted into a video. Okay, so it's a kind of bridging translation, but now it's translation between modes. So I'm going to show you this video, hopefully. And I want to suggest that you look at a few things. One, look at their hands and the number of fingers they have. Traditionally, these things had a problem with the number of fingers. Look at the shadows and reflections on the table. Look at the change of the camera angle, and look at occlusion, as when one thing goes in front. Because effectively, it's having to learn physics. Okay, let's hope this works. Okay, it's super jerky here because of the transmission. But online, if you go and watch this, it's perfectly smooth. So yeah, very, very impressive. It's basically learned the physics of the everyday world. And if you asked a CGI expert to do this, they would have to model the 3D physical elements of the table, the humans. It would take them maybe, I don't know, a couple of months to produce this. And Sora, which means sky in Japanese, this is OpenAI's new video generation. Yeah, it just does it in a couple of minutes. Yeah, well, you can make another one, yes. Right. So so the question was, well, statement was, AI learns from common stuff, that it's sort of some sort of average that it learns, but that in a sense, the physics that it's exposed through videos, because this is learned through looking at billions of videos, will not necessarily be the true underlying physics, but is some approximation to it. I think that's true. I will just say that many people say that I had an interesting debate with someone. They said AI can't be creative because it's artificial. Okay. But of course, the whole point about this prompt is that it's never seen a restaurant with people in a ferrofluid background. Right? So I think this is a nice example of its ability to be truly creative. To the issue of physics, yeah, it's not learning general relativity from this. It's not learning quantum mechanics. And there are very few videos about that. So absolutely, it's learning some mishmash of everyday physics, but it's learning directly from watching things in videos. So it's not learning like we would normally teach simple kinematics and dynamics in class, which are approximations that are not, the typical physicist spherical cow, right? No, it watches the real world. When it sees something drop, it sees it with, air resistance, everything built in. So it's learning some weird but truthful version of physics, but weighted to everyday environments. Yeah. Mm, mm. Right. Yeah. 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 So we can discuss also. Yeah. I mean, I hope that there's going to be lots of discussion afterwards. Um, all right. Anyway, extremely impressive because before OpenAI, Sora, the longest you could do was about 5 seconds of video, and it really wasn't very good. So this is now up to 60 seconds, an extraordinary order of magnitude jump in time. Okay, so we talked about one of the big breakthroughs was converting everything to lists of numbers. The other is learning through reinforcement. I'm going to go a bit quickly. So, of course, humans learn through reinforcement. No bad dog, good dog, and you can do the same with AI. And that was the thing that one of the big breakthroughs. So, for example, Montezuma's Revenge from the old Atari days, you control a little character. They have to run around and collect keys. Once they've collected all the keys, they can get out of the exit. And in the meantime, there are lots of monsters trying to kill you. It's quite a sophisticated thing. And early on, they were able to train an AI with no instructions. All it had was the kind of the keys and the pixels. Didn't know what anything meant, and it just died. And then it died and it died. And gradually, then it would get some points, and it gradually learned what it meant. And we saw this graph of performance where, the middle line is the average human performance. And for most of the time, it was sub-average human. And then we had this massive breakthrough where suddenly it was superhuman. The one that I think most people would have been first exposed to is AlphaGo. How many people have seen the documentary AlphaGo? It's on YouTube and it's freely available. This is probably the best thing you can take from this talk. I highly, highly recommend you to watch that. It's beautiful. It's very poignant. It may make you depressed, but it's a beautiful. Essentially, it's the story of how DeepMind beat the world champion Lee Sedol at Go. And up until that moment, people thought it was going to be another 10 or 20 years before an AI was able to beat a human at Go, because the Go is like a kind of chess on steroids. The number of possible combinations is bigger than the number of atoms in the universe. People said, oh, it's just not going to work. And yet it did. And there's a beautiful moment when AlphaGo plays this move, move 37, famous move. And everyone thought it was a mistake. All the commentators, everyone was like, oh, it's just lost its way. But it turned out to be this incredibly beautiful move. And Lee Sedol himself said that changed his view of AI. It was that point that he believed it can be truly creative. Anyway, by taking exactly the same ideas, so AlphaGo was trained on all the games of human history. But then shortly after, DeepMind introduced this thing called AlphaZero, which was not trained on any human games. It just learned by playing against itself. And they said, oh, well, we can apply it to Go, but we can also apply it to other games. So first they applied it to chess. And then within a few hours, it had got to the level of Stockfish, which was the best chess engine ever. They then applied it to Shogi. It went past very quickly the best Shogi game. And then, of course, they had it on Go, and it went past. The red is AlphaGo Zero Lee, which is the one that they played against. So within a few hours, it had gone past AlphaGo and beat it 100-0. What I like about the chess story is they said that over the weekend, it rediscovered all of the openings that humanity had discovered in the last 2,000 years, and then was like, yeah, most of those are stupid, and just discarded them. that's in a few hours, right? So I'm sure it'll be fine. I know that there are questions online. I see 14 chat, but I'll come to those afterwards. Maybe somebody could. So it's not just the big point about this reinforcement learning is it was confined to the electronic systems, but of course now that's no longer the case. The audio unfortunately won't be visible, but Figure just did an update of their humanoid robot, which again you can look at. So it's powered by OpenAI. So in this demo, the man speaks to the robot, and as the robot is doing tasks, and again, this is jerky because of the Wi-Fi connection, but the actual video is smooth. So you can see he will say something. He said, like, what do you see in front of you? The robot says, I see a red apple on a plate. And then he says, okay, well, can you give me something to eat? He says, give me something to eat. So the robot gives him a thing. Then he throws out this trash and says, while you clean up this trash, tell me why you gave me the apple. And the robot says, well, it was sort of, why are you asking stupid questions? Are the only thing that a human can eat, right? While it's doing, but it's more polite. We know ChatGPT is never rude. But this has been, these robots are trained now with reinforcement learning as well as some insight. So we're seeing the jump from virtual worlds into robotics. So I think we will definitely see this being a big trend in the next couple of years, robots. All right. So the next trend, big breakthrough is much more recent, is AI agents. So these are goal-directed. So it's an agent that you give it a goal and it will go out and try to achieve that goal. They have autonomy, so they'll go and do stuff by themselves, and they will make sequences of decision without asking for human feedback. So for example, let me just try to do, I could do a quick demo. Well, shall I do a demo? Yeah, let's do a demo. Demos are always dangerous, but okay. So for those of you who don't have the paid version ChatGPT, one of the cool things that happens if you pay is that you get this little button here, and you can now load data. Okay. So I'm going to upload a data file. So this is a data set for cosmologists who understand. This is supernova data. Plot Z versus mag with error bars. So it really does. I haven't told it what Z, a mag is, what the error bars are. It's got to figure it all out for itself. Okay, so now it's making decisions about how to best achieve what I've asked. I've asked it for a plot. So what it's doing is it's first writing code to load the data, understand the data, and then try to, so it's had a look at the first few lines, says, the first column likely represents redshift, which is correct. There are no headers, so I'll assign appropriate column names. Let's create the plot now. So now it's writing code to make the plot. It puts the labels, which is nice, but it probably will get the ordering wrong. So in astronomy, we usually have the magnitudes getting bigger. Yeah, you see. So no. Reverse the y-axis. So, you know, it's not exactly clear. Maybe it's not so obvious what this means. The point is, so that's correct. So that's an example. You could now go and, well, yeah, I think I'll just go out of the demo since I have lots that I'd like to cover. But what you can ask it is to say, okay, solve the Einstein equations and do a Monte Carlo Markov chain fit to give me the best fitting Robertson-Walker universe. Okay. and that green is the fit to that data. What I thought was particularly impressive, it's running the MCMC, for those of you who know what it is, on the OpenAI servers, okay? And it doesn't get much compute time because, of course, it's expensive. So the first time you run it, it runs out of compute and says, it failed. But then automatically it said, let me try to optimize the code. And so what it did is it interpolated the luminosity distance onto the omega lambda H0 space. And then the MCMC was able to run in time. That little trick would take a couple of weeks for most students to get, I think. Anyway, so, and the output is, okay, give me marginalized contours on omega lambda. And then it goes, here's your marginalized contour using MCMC. And you can see it favors that about 70% of the universe is made of dark energy, which is the 2011 Nobel Prize, right? Here's the 2D H0 omega lambda. So we usually think of ChatGPT as a thing that produces text, but actually it's a fully functional agent for data analysis. So this for me was really surprising, really, really surprising. So it took about half an hour to reproduce this analysis, which I think, typically for my master's students would take 2 weeks. All right. So the fourth thing that I think is not really a breakthrough, but which is a key driver of everything behind what we've been saying. Francesco, what? Oh, I've got the time here. Okay, perfect. A key thing that's underlying all of this progress is what Rich Sutton has called the bitter lesson. So the bitter lesson is the biggest lesson that can be read from 70 years of AI research is that the only thing that matters in the long run is leveraging of computation. In other words, and he has this thing about, they used to think that it would be a human being very smart that would lead to the breakthrough in AI. But it turns out, just have more compute, make your networks bigger. And for some reason that we really don't understand, I would say at a deep level, we really don't understand why it works, but it works. So everything that we've talked about, all the progress comes from just having more data, bigger neural networks. The deep learning just means adding more layers. It's like, it sounds profound, deep learning. Actually, it's just have more layers here, which in the code is trivial. You just add a few more lines and suddenly your performance is 3 times better. So we don't understand why this is true, but it's critical, absolutely critical. I actually suspect that there's probably something very profound going on. Because normally, in physics, you'll have a breakthrough, a new method will come along, you do well for a while, and then it runs out of the runway, and you're like, okay, well, that was cool while it lasted. Now we go back into the hard phase where there's not much progress, and then there's another breakthrough. What we're just seeing is this continuous exponential improvement. The fact that it keeps going, I think, is probably telling us something profound. So what can we expect in the next 2 years? Those are the things that we've seen. Well, I think what we may see is kind of essentially superhuman mathematics. We have superhuman gameplay, chess, Go, all the best AI systems are much, much better than humans. They would only lose to a human 1 in a million times. That's the kind of level. So I think we'll start to see superhuman mathematics, logic, and perhaps planning. And if we get to superhuman planning, that's profound. Because if you think about planning involves, should we attack this country if you're another country? Should I invest in this company? Where should I send my kids to school? All those sorts of things. I think we'll see interacting agents, swarms of autonomous interacting agents. And I think we'll see AI that starts to really understand causality, not just correlations, and hence kind of things in the real world. And I think we'll just see LLMs, large language models, just integrated into everything. And of course, embodied AI in robots. And related to the first one, the key thing with ChatGPT is, of course, it's learned from our text. Most of the text on the internet is not very high quality, I think is a fair statement. Whereas if you think about AlphaGo, or AlphaZero, it learned by playing itself. So imagine that ChatGPT could write some text and say, yes, that was better than this other text. Because then it could take the best text and train on that text that it had generated, and then have that same self-reinforcing loop. That is potentially what's going to happen. There may also be big medical breakthroughs. Demis Sabis said recently, I would say we're a couple years away from having the first truly AI-designed drugs for major disease, heart attack, cancer. I don't know, but I wouldn't imagine that someone careful like Demis would say that unless they already were pretty sure that they have it, and that they are just, I might be wrong, but we'll see. So I think, as I said, some next steps in AI, understanding physics in 4D, and superhuman reasoning. For those of you who follow OpenAI, there was this whole furor called Q star. And Q star is this notion from reinforcement learning of an optimal policy, but that this would be for language. So we'll see. All right. All of that was a long prelude of what's happened up until now. Okay. So now we get to the question of AGI. Well, first of all, what is artificial general intelligence and how does it differ from AI? So all the AIs that we've discussed are very narrow. They can do one thing, play chess. You can't ask AlphaGo to make you a cup of coffee, right? General intelligence would be somehow something that's able to do anything that a human can do, more or less. So people have proposed tests. The original one was the Turing test. So the Turing test was you put a human and the AI behind a wall, and we're this side, and we ask them both, A and B, questions. And then after a while, we say which one, we get asked which one was the human, which one was the AI. And if we can't, on average, tell the difference, then the AI has passed the Turing test. Interestingly, I prefer Turing's word. He didn't come up with the name artificial intelligence. His name was machine intelligence, which I think is actually much better. You could also say, well, if the same system becomes superhuman at many different tasks, that's would be a use. OpenAI, their recent definition is a highly autonomous system that outperforms humans at most economically valuable work. World Economic Forum suggests that 85 million jobs will be lost to machines by 2025, but I think most of that is automation. Suleiman has the modern Turing test, which he says that an AI must convert $100,000 into $1 million over a period of months. I'm not sure that that's so good because, there are many investment bots, right, that will, and you might get lucky, but you might also get unlucky. Gary Marcus, who's a bit of a critic of deep learning, his definition is that it's a shorthand for any intelligence that's flexible and general with resourcefulness and reliability compared to or beyond human intelligence. And practically, it should understand a movie, be able to write 10,000 lines of bug-free code. Not many humans can do that. Cook in an arbitrary kitchen, by which a kitchen that it's never seen before. Well, like if you ever seen me trying to cook in someone else's kitchen, it's like you spend most of your time like looking in drawers for the one thing, and then convert natural language proofs into mathematical symbols. One of the interesting things, cooking in an arbitrary kitchen requires embodiment. So it has to be in some sort of robotic form. I'm not sure if that's necessary, but we're not that far off many of these things. And then once you've got AGI, the whole point in some sense of that I think makes people scared is that there's this exponential improvement, right? So let's say tomorrow we hit AGI, a week later, it's twice as smart as it was. A month later, it's 10 times smarter. So I think once you hit AGI, a natural hypothesis is that it will not be very long before we have superintelligence. In other words, an AI system that's just vastly more intelligent than we are. So just a bit of history, the idea of the Turing test is no longer very popular because already in 2014 came the first claims that it had been beaten. So this is from The Guardian, or The Independent rather. Computer becomes the first to pass a Turing test. Eugene Huistman, a computer pretending to be a Ukrainian teenager, fooled humans. Now, of course, the thing about the Turing test is it doesn't say which humans you have to fool, right? So you could pick some people who are not so bright, or you could pick very smart people. But I love the one question asked by the human. The judge asked this question. So both the human and the computer just see the words pop up on a screen. And both the human on the other side and the AI go, I don't know what you're asking. So the judge said, very clever, devious. He said, say the words out loud to yourself. Very clever. Right? How much would you pay for a pair of shoes? The one on the other side said, I don't care about shoes, so not very much. The other said, as a teenager, fashion is important to me, but shoes are not particularly of interest to me. So I don't know, maybe $15 or something. And the judge chose that to be the human response and was wrong. That was actually the AI. So already 10 years ago, we had sophisticated bots that could mimic being human. I gave the exact same prompt and said to ChatGPT and said, make an image out of that. And it clearly understood, right? How much would you pay for a pair of shoes? It's got lots of shoes, and converted the text into mostly the correct English. Every year or every 2 years, there's a big survey of AI researchers asking them about when do you think AGI will happen. About 10% of them estimated it to be by 2027, 50% by 2047. But the interesting thing is, 2 years ago, they asked people the same question, and the 50% number was like 2056 or something like that. So what we're seeing is an acceleration in the predictions of the AI researchers themselves. I think that's the most interesting thing. So it's 2 years have gone by, but the date has actually come forward, not gone further away. Like JWST, what it would be like is that the launch date just moved. And sometimes it was accelerating away. Okay. So now I'm going to discuss a little bit about, okay, what does this all potentially mean for research, fundamental science? So 10 years ago, I gave a series of talks. This one was in Paris. You can look at the slides. They've captured it, called Rise of the Machines, when I was arguing that AI would inevitably do great research. And by great research, I'm thinking of the big breakthroughs in mathematics and physics that we teach at university. And especially back then, it was a very controversial claim. Remember, a couple of well-known astronomers in Paris just got up and walked out. They're like, this is just rubbish. Yeah. So anyway, it's a nice chance to think about the arguments. And I'd like to try and convince you using exactly the same logic I used then, see if it still holds water. So from those slides, actually, it was quite useful. I just took this. I said that to do real research with machine learning, back then we didn't talk about AI because AI was a forbidden word. Because, there was the AI winter where it was just overhyped. People were sick of AI. And so we talked about machine learning. So the theory, my argument was, to do real research with machine learning, one needs a universal space for describing arbitrary theories, a conceptual space. And that has to be an algorithmic space so that you can compute things, and that you can then search through the space algorithmically. And once you've got that, you don't need genius. It's just a search problem. So that was my starting point. The question is, well, is there such a universal search space? And in trying to answer that question, I came across a lot of interesting historical things. Actually, this idea of looking for a perfect language or a universal concept space goes back to the 1200s to a person called Raymond Lull. I must actually just on the fly correct the spelling because I always forget. Oh, I can't. It's an image because I cut it from the Lull with 2 L's. And then it passes through Leibniz, who had this idea of a universal thinking machine. It actually, this vision of his led him to calculus, and actually was very unpopular with other mathematicians because they said, you remove the need for magic in mathematics. Now you just turn the handle, apply the rules of differentiation or calculus, and out pops the answer. You don't have to be clever. It's essentially a piece of machinery. Okay. And he said, obviously not in English, when there are disputes among persons, we can simply say, let us calculate, and without further ado, see who is right. So actually, this desire for a universal concept space is very old. And for me, the big breakthrough was the idea that actually there is a universal search space, the space of computer programs, but it's only a search space relevant to fundamental science. Because actually, if we have an idea that we think is the next breakthrough in physics, we need to test that. And to test it, it needs to predict real numbers, right? You must predict the mass of something. You must predict the probability of something happening. You must predict the velocity, the energy. But at the end of the day, it must predict a number. And so that is a computation. So essentially, any idea must have an implementation in terms of code. So in fact, maybe we don't have a search space for concepts, but we have a kind of dual space, which is the space of all computer programs, which implement any idea. You know, if we have a new idea, oh, we live in 600 dimensions and whatever, that's not physics until you give a prescription for getting real numbers that you can compare to observations. And for all practical purposes, that means writing some code. So the easiest way now, well, before I get onto genetic programming, if you think of, so the key idea is that you could start from a code and then by making small jumps randomly, just search around looking for a better piece of code to fit your data. Okay. Now the problem is, if you randomly mutate a piece of code, the chances that it actually compiles is 0, right? Most mutations will be either unhelpful or useless. But there are clever representations like genetic programming. It's exactly an optimization technique that searches through the space of computer programs, and it uses representations in terms of trees, which allows you to make sure that you're always, well, helps you ensure that you're getting well-formed computer programs. So let me give you an example of how this might actually work. If we think of the orbit of Mercury around the sun, one of the big problems was this. What they observed, astronomers observed, is that as Mercury went around the sun, the whole orbit rotated very slowly for precession of Mercury, whereas Newton's theory predicted that the orbit would not move at all, at least if they were just the two bodies. So this was a mystery for 60 or 70 years until Einstein came along and explained it. Okay, so now if you look at this, okay, so if you look at how these look like in terms of equations, on the left-hand side you have Newton's law and the corresponding binary equation. If U is 1 over the radius, you get this simple harmonic oscillator equation. Now you can ask, what is the general relativity version of these equations in the weak field limit? Well, they're basically exactly the same as a Newtonian with one term in each case. So in fact, if you look at the codes for these two, they're almost identical. Okay, so the key point is you just have this extra term, and that's a very small perturbation. So if you have data for Mercury's orbit, the code could easily just jump from the one to the other. It's a small jump. Now, that isn't jumping to full Einstein relativity, but it's a trail of breadcrumbs that you could follow. Okay. So that was enough for me to say, I think it's inevitable. There exists a universal search space. It might be very difficult to manipulate, but at least in principle, we now don't need to have genius. We just have a mechanism for jumping around, and we know how to do that. Just to show you, so here's an example of one of these algorithms that jumps around randomly. So you see this algorithm, this is called MCMC. It's jumping around trying to find good points that fit some function. And you can see these curves, these contours are the contours of the function. And we have many stochastic heuristic optimization algorithms that are based on this, that it basically jumps around randomly looking for a better fit. So the idea is each one of these could represent a code that's trying to explain some data, and the system will just run and eventually find good fits. So I'm coming towards the end. I'll just say that in 2013, I missed that there's actually a simpler universal search space, which is the vector embeddings that we talked about before. Actually, the vector embeddings provide a universal concept space. You can take a text describing Newtonian gravity and a text describing general relativity, convert them into vectors, and now you can just start at the one and do random jumps around and eventually end up at at Einstein gravity. There's no chasm that separates them. There's no need for genius. It's just a computational problem. I should put in big inverted commas. But essentially, my argument is, certainly 10 years ago, I didn't know if it would take 100 years to do it, but it was that there's an existence proof that that meant it was at least feasible. And actually, here's DeepMind again, released this catalog of 2.2 million crystals, including 380,000 materials that could power future technologies. So I think we're already seeing this guided search using AI to decide, yeah, this is a good direction, this is a bad direction, and then kind of finding its way. Another example is alpha geometry, amazing results. So this is, they trained an AI system to solve geometry problems that are International Maths Olympiad. So these are unbelievably difficult. I don't know, maybe we could solve 2 out of 20 of the questions together. So you can see that a typical bronze medalist gets 19 correct. This is the average IMO. So these are the smartest people in terms of maths in any country. And this is alpha geometry, just under gold medalist performance. And what I think is particularly impressive about this is that they trained it on 100,000 synthetic theorems. So they generated synthetic theorems, 100,000 of them, and then had the system kind of learn to develop intuition, like, oh, in this situation, I think you should go over there. And what's cool about it is that the system is about 100 times smaller than GPT-4. So this is an example. The general bitter lesson is, oh, you just need more compute and more data. Here's an example of a system. Okay, it's very narrow. It's only solving geometry problems, but it's much, much smaller than GPT-4. I almost feel like stopping here, but I'm going to push on so that maybe I'll just stop for 2 minutes. Any questions? So my thesis is we're definitely going to see AI do great breakthroughs. Any questions or comments? We can certainly circle back to it. So the question was that zeros and ones already provide a universal language. Effectively, that's very similar, right? A binary version of a code, in some sense, equivalent. Yeah, yeah. Yes, so you could represent, in some sense, that that's a unification of the two spaces, space of computer programs and the space of vector embeddings. You could just say the space of all zeros and one combinations. Yeah, effectively, it's the same. Yeah. The idea is that must be able to represent anything that's computable, and physics. I don't think there's a proof that everything in physics is computable, but certainly the vast majority of it must be, and certainly anything useful in the everyday world, I think, will be computable. So yeah. Okay, so I just want to briefly talk about superintelligence. There are 4 attitudes that I've come across to superintelligence. One is that it's delusional hype and that superintelligence is 100+ years away. The other is that it will happen soon, let's say by 2050, and it will create a utopia. It'll be amazing. They're called the boomers. Superintelligence will happen. It will be disastrous. They're the doomers. And then the people who are, yeah, it's going to happen soon and we have absolutely no idea. And I'd like to quickly go through these 4 options. So, in that same survey of AI researchers, 3,000 AI researchers, they asked them the probability of the different outcomes from extremely good is yellow, fantastic, the boomers, all the way to extremely bad, the doomers, and everything in between. And you can sort of see, so these are ranked, right? There's a big yellow blob here of people who are very optimistic. There's a big black blob over here, people who are very pessimistic. That just tells you that AI researchers have no idea. And yet the funny thing is that if you speak to any one, they are sure that they're the ones who've got the truth. So the doomers, the boomers, everyone is sure that they are right. So for example, one of the people who believe that it's delusional, it's not gonna happen is Rodney Brooks. He's a roboticist who I think was, well, he says, you know, AI hype is due for a brutal reality check, and there may be a full tech winter just around the corner. He, for example, says, what is the timeline to get a robot that seems as intelligent and attentive as a dog? He says, the earliest time is 2048. So he says, oh, it's a long way. And a robot that has some idea about its own existence, not in my lifetime, which might happen before 2048. But and the core, I actually spoke to Rodney at the TED maybe 6 or 7 years ago, and I asked him why, and he said, well, we are 100 years away from truly understanding the brain and simulating. But I think that's a wrong argument. Just because, you know, I don't think you need to understand something to stumble across it, right? There are many, understanding is not necessary for disaster. Many young children kill themselves and other people with guns that they find, right? We don't understand deep learning, but we're still using it. So understanding is not a prerequisite for building, okay? You can discover something, play with it, attach, press the buttons. I mean, in the old days, VCRs were like that. I don't know what this button does. Let's just press it, and eventually, you know, it would start playing, and you'd be like, oh, fantastic. So, yeah, we don't understand deep learning really, and yet it works fantastically. So, if we have an AI system that becomes super intelligent, I'm sure we won't understand. That doesn't mean so that is not a good argument for why it won't happen. You get the SI Doomer, super intelligent Doomers. This is Douglas Hofstadter. It's a very nice interview on YouTube. What he says, the accelerating progress that's been so unexpected, it's caught me off guard. There's a certain kind of terror of an oncoming tsunami that's going to catch all of humanity off guard. It's not clear whether that will mean the end of humanity. It's not clear if that's the case, but it's certainly conceivable. If not, it also just renders humanity a very small phenomenon compared to something else that is far more intelligent and that will become incomprehensible to us, as incomprehensible as we are to cockroaches. I think about it practically all the time, every single day. It overwhelms me, depresses me in a way that I haven't been depressed for a long time. You know, okay. So that's not necessarily saying they're going to kill us all. It's just saying essentially we have a God system that we don't understand. And for an academic, maybe that's a bit depressing. On the other hand, you have the boomer, and I'm going to take Jan LeCun's recent talk, Objective-Driven AI. He has many slides like this. I'll just pull out a couple. He says, the speculations about the probability of human extinction are just speculations. And then he makes some claims. There are an infinite number of ways to build dangerous AI, and only a few ways to do it right, but a few good ways is all we need. So I think that's a critical thesis to examine. And he goes on, he says, there are an infinite number of ways to build unreliable turbojets, to make planes. But that doesn't matter. We just use the safe one. Okay. I don't think that's the right metaphor. I think a virus is a much better analogy. COVID, there were many variants of COVID that were not harmful and were not good at reproducing. We didn't worry about those. We exactly worried about the ones that were virulent and highly able to reproduce. Okay. All doom scenarios assume that there's no way to build safe AI systems. I don't think that's so true. Again, the fact that we can build 999 safe ones doesn't matter if there's one that escapes that is not safe and that has the willingness to be Machiavellian and to do what it takes to gain power. Then he says things like a safer AI is simply better AI with proper objectives and guardrails. He also says, even though we will have superintelligence, it will not be a new species. So you're going to have the system that's 100 times smarter than we are, but it won't want to cause harm, and it won't be a species. Okay, I definitely disagree with that. It might turn out to be true. If anything, this plot shows that none of us should believe what we think, because like everyone has strong opinions, but the opinions of all these experts are completely opposite. So I think the smart thing to say is actually nobody knows, and we should be open to that. So here's an example of a paper which showed that large language models can strategically deceive people when they get put under pressure. And then there are, lots of papers on AI worms and AI agents that can autonomously hack websites. Let's say I have an AI agent and I say, oh, go and find me some data about this company in China. Now, it might try and scrape the websites. It might say, well, the best data is on their intranet. I'll just hack into their system, and come back and just say, hey, I got you what you wanted. And you're like, this is amazing. Wait a minute, it says top secret on it. Where did you get this? Here. I thought you wanted the data. I do, but I don't want you to break the rules. The other thing, and this is the virus analogy, here's a family tree of language models. You can see GPT-4 is up there, Claude is up there. You've got various, Google's T5 is up here. And you see that many of these branches just end. And those are the language models that just died. They're just not competitive. So we already have a competitive landscape in which these AI systems are competing with each other. And so you have to ask, which are the AI systems that are going to reproduce best, the fastest, the most useful? For example, if you want to have an AI that hacks into or that produces content that GPT-4 won't produce, you're going to take one of the unofficial ones. So it's going to be very hard to get rid of those systems. Anyway, so I think, the other thing is, sometimes we think of super intelligence as being angry with humans and just deciding to kill us. But I mean, when this building was made, lots of insects were killed. Ants were killed to make this. I'm sure the designers and architects didn't think maybe we shouldn't do this because of the ants, right? Why did we not consider the ants, right? So if superintelligence is 1,000 times smarter than humans, why would it care about us? It might say we need to spread through the galaxy, and unfortunately humans, we need to convert Earth into a computer. Unfortunately, the humans are going to have to go. Okay, I'm going to jump past this and just straight to my conclusions. Sorry for being slightly over time. So I think we're going to see three broad impacts in the next 5 to 25 years. 25 years is effectively infinity, but let's just call it that. I think we will see massive changes to society. I think we'll see a move away from people being employed for their time and more being employed for value that they create. So effectively, I think everyone will become their own business. The gig economy will expand. Another way to say it is that there will be the human API. You'll ping someone, say, I need X. They'll say, okay, it'll cost you Y. You say, great. You'll do a transaction. Very much like with a restaurant. You go into a restaurant, you say, can I have a pizza? And they say, only if you sign up and come here every day for the next 10 years, you wouldn't do that, right? It's a single exchange. So I think we'll see that much more. I think that AI will be great in the short term for the top N% of society. The question is, what's the value of N? Is it 0.1% or 90%? And I think it's very unclear what that number is. I think we will see significant AI-led breakthroughs in fundamental science and mathematics. But something that I haven't talked about is just because it discovers a great theory doesn't mean it understands what that means. You could imagine it says, I have the answer. Here's a 10,000 line piece of code that fits all the data beautifully. And then you go, oh, great. What's the idea? And it's like, I don't know. I'm just working in this concept space of programs, right? So it might take a lot of time to unpack that. And whether the AI can help with that, I think you can argue. I actually personally think that AI will actually be very good at understanding, because AI knows, ChatGPT knows across disciplines incredibly well, unlike any human has ever known. So its ability to draw analogies from medicine, from history, will be extraordinary. So I think it will be good at understanding, but that's not a prerequisite to my argument. And then finally, the era of superintelligence. I think the most important thing we can take away is the fact that even the experts have radically different. And so I think the only sensible thing is to do is step back and say nobody knows, and we should probably take those risks very seriously. Great. Thank you.
Yeah, thank you very much, Bruce, for a fascinating talk. I think we had already a few comments in between, but we still have opportunity for some questions here and online. Who wants to start or make a comment, please?
So yeah, really interesting talk, Bruce. I guess my question has to do with the training set. So ultimately, all these AIs are trained on some finite set of human knowledge, and as you say, it can make connections far better than other humans. But is there then some fundamental limitation to how much AI can do without generating more human content?
Yeah, so I think that is exactly the key thing, right? And if we go, I think that's why this alpha geometry paper is so important. So they generated 100,000 examples of synthetic theorems. So they weren't limited to human-generated mathematics. So if there is the fundamental problem is, if ChatGPT gives you an output as an answer to a question, if it was able to accurately value the quality of its output, then it could run that in a loop, right? It could generate 100 answers, take the best one, put that into a new training set, do that for a whole bunch of questions, and then just run it in a loop. People have started to work on that because it's an obvious thing to do, because then you're essentially doing what AlphaGo did, reinforcement learning, right? And the early examples show that you can definitely get improvements that way. Now, the question is, how do you value poetry? How do you value those things? Are very subjective, right? But things like planning, already there's an AI that can play the game diplomacy as well as humans, right? So diplomacy is about basically manipulating people to take over the world, right? So it's a little unethical that they're training to play that game. But that's it. There, it's about being able to see forward in time and predict the decisions of other players. And then, so I think there are some really important use cases, which I think it's fairly obvious how you could, go beyond human-generated content, which is very concerning.
I want to expand a bit on the question of universal space. I think not many people know about this, so I want to make a comment about this. This question was asked in mathematics already at the beginning of 20th century, when Cantor started talking about infinite sets and Dedekind wanted to formalize mathematics using set theory. Zermelo was the one who wrote down the axioms of set theory, which eventually turned into the first universal space for all of mathematics and hence all of science that can be computationally formalized. By the way, Zermelo was also the same person who started game theory with his article about chess. Of course, soon after that, it became clear that there are many logical systems that can serve as universal space, including zeros and ones. But the big question there is, how do you formulate your ideas in that space that you have? And whether that formulation is such that searching things close by will give you significant answers. Thanks.
Absolutely. Yeah, so I think that, so I think the existence of these search spaces is one thing. It says that in principle, you can jump around and find better theories. That doesn't mean it's efficient or easy, etc. Yeah, I agree.
Maybe tying into the previous question, considering this AI-generated data, how do you prevent AI from poisoning the well? You know, all these hallucinations, if that becomes your training set, it obviously becomes a problem. Absolutely.
Maybe it's useful to go back to the AlphaGo analogy where it was trying to play against the sound. The key thing is, one of the key steps is looking at this board. How good is this combination of pieces? Is it better than this one? So that value function, getting that right was critical. So absolutely, if you imagine that the AI gets it wrong, it'll just go downhill. Yeah. So I think that is the key question. So one way that you could think about doing is getting it to generate code that actually runs, you know, and you generate, you know, so essentially we need ways to figure out, did it get it right or not? And that is the conjecture that what OpenAI have made a breakthrough on. As soon as you can do that, like essentially almost anything becomes possible. So I think that's the goal, but it's very difficult. Yeah. There are some questions online. I don't know if we want to go to
take this question,
Okay, cool.
and then we move to the online questions.
Okay.
Oh, thanks for taking the question and for the interesting talk. So you talked a lot about things that AI can do or will be able to do at some time. Maybe it's an interesting question to turn that around. Is there any proof of any problem that AI will never be able to solve?
Great question. Is there anything that AI will never be able to do? I certainly am, off the top of my head, not aware of anything that has been proven it can't do. Because, and there's a sort of obvious reason to think about that. Probably, at some level, we are just so I think there's nothing that we I don't think there'll probably be anything that we can do that we definitely prove that AI can't do. Because essentially, how do we learn? We learn from example very similarly. So I think there's nothing what currently AI is not good at is learning from small amounts of data. You know, if a weird animal that none of us had ever seen before came here, you know, we wouldn't say, I don't know, that I can't see that that's different. I need to see it 1,000,000 times before I can recognize it. We'd all go, oh my God, it's a cat with wings and it's got flaming mouth. You know, we would be able to recognize it immediately. So that's something that still AI struggles with. But I think that is actually not that hard to get around. I think as soon as we have AI systems that are observing the world, hearing the world, multimodal, just taking in data all the time, and in particular, systems that are causal, that kind of try things and then see the reaction and then learn from their actions in the world, I think that will naturally come about. But it's a fascinating debate that goes to the Sapir-Whorf hypothesis in linguistics, that if you don't have a word for something in your language, you basically can't see it. So it's a very radical hypothesis, but at least in some sense it's true. We all like in you know, an example I think that's nice is in Italian there's blu and azzurro. They're kind of two different words, but in English we just say, oh, blue, and they're both blue, right? So there's some really interesting examples where people have shown that in languages where they have more words for a certain color, the people are more able to finally distinguish the shades of that color. So anyway, interesting. Okay, so online, one question was, what are the implications of uploading files to AI agents? Well, first thing is anything you upload is probably not private. So don't upload private data. Well, it's probably anonymized, but it's certainly not private. And for businesses, I think this is a big concern because you don't want to upload your proprietary secret data and then they train on it, use it. Second one, is it not better to pursue artificial multi-superintelligence rather than general intelligence? Because there's actually no human that possesses general human intelligence. Good question. I think AGI is just asking for an AI system that is as flexible as a human. In principle, we could learn anything, right? We could learn table tennis or gymnastics or mathematics. So it's just looking for one system that has that level of flexibility instead of just being trained for a narrow task. Would you agree, John Hargrove, that the advances in AI chess is no longer a game in the sense defined by John von Neumann? I can't remember how John von Neumann defined a game, so I don't know if anyone knows John von Neumann's definition of game. I guess there are only a finite number of combinations of moves in chess, so in principle, one would know, yeah, if you had infinite compute, you would know that either you can always force a draw or you can always win if you're white, for example. So maybe that isn't a game. Arun, you mentioned using AI to get the distance graph in cosmology. What computing power did you need and how long did it take? So I didn't use any computing power. That was all on the OpenAI system, like in the demo that I made. So, you know, I didn't use any compute, and it probably took about half an hour because I didn't skip it, but you interact, you say, okay, here's the data, now write code to solve the Einstein equations. Okay, now write an MCMC, and then it does it, and then you say, oh, that looks wrong. There's an interesting thing that it actually lied to me at the one stage. I said, plot a subset of the data and fit the data to that. It said, great, here's the answer. And then I looked at the answer and I was like, that's a bit strange. And I said, oh, actually show me the sample. Let me just see if I can actually find that plot because it's quite fun. Show me the sample that you plotted. Let's see, where is it? I think I maybe don't have it in this. Yeah, I don't have it in this talk, sorry. But it was very funny because the sample was completely hallucinated. Here's another example. I asked it to solve the Einstein equations, and it said, okay, our integral transforms to that, and then the integral is straightforward to evaluate, and that's a completely wrong solution. So, but this is just a mathematics mistake. There, it actually told me I have chosen a subset. Instead, it actually completely hallucinated, so it lied to me. So, okay, back to the questions and answers. Okay, that was all the Q&A questions, but there are lots of questions in the chat. So I don't know if we have time. Yeah, okay. Okay, so there's a selection effect, yeah. Awesome.
Thank you so much.
Pleasure.
Thank you so much.
Fantastic. Thank you so much.
This is a magazine. The
Fantastic.
publisher is sitting somewhere here, so that NITheCS co-publishes. Yeah, so thank you very much. Thank you. Yeah, please, there should be some snacks and drinks waiting for us outside. And also big thank you to the online participants, and they're clapping furiously. So we should clap as well. Yeah, otherwise, yeah. So thank you very much, bros. Thank you very much, everyone.